Right now, as you are reading this, Earth's magnetic field is absorbing the second of 3 separate eruptions that left the surface of the sun inside a single week. The first has already washed over our planet. The second is unfolding as we speak. The third is still crossing the 93 million miles of space between the sun and Earth, and scientists at multiple space weather agencies are calling it the one to watch. 3 solar storms from the same region of the sun, arriving one after another in rapid succession. That is not an everyday occurrence. And the reason researchers are paying such close attention is not simply that these storms exist. It is what happens when a magnetic system that has not finished recovering from one impact gets hit by another and then another, and what that stacking effect could mean for the satellites, the power grids, the GPS timing signals, and the communication networks that almost nobody thinks about until they stop working. Today, we are going to walk through this completely. What these 3 storms actually are, how a calm-looking sun produces something powerful enough to knock out infrastructure 100 years later than it was built, and what the specific danger is when storms arrive back-to-back rather than one at a time. Then, like always on this channel, we are going to widen the lens. We will look at the historical events that give this week's activity its context, the vulnerabilities in modern infrastructure that most people have never had explained to them clearly, and a grounded, practical answer to the question everyone eventually asks, which is simply, should I be worried? And if so, about what exactly? No exaggeration, no doom framing, just the mechanics and the stakes as they actually stand. Quick question for the comments before we start. If you have ever seen the Aurora somewhere it does not normally reach, tell me where you were and what it looked like. Strong geomagnetic activity pushes the Aurora down to latitudes that almost never see it, and some of the most memorable sightings came from people who had no idea it was even possible where they lived. I read every comment, and if this kind of grounded science breakdown is useful to you, subscribing helps, because it tells the platform to put this in front of more people asking the same questions. Let's start with the sun itself, because none of this makes sense without understanding what is actually happening on its surface. The sun is not a static ball of fire. It is a sphere of plasma, an electrically charged gas, held together by gravity and powered by nuclear fusion happening in its core, where hydrogen is converted into helium at a rate of roughly 600 million tons every second. That process releases an amount of energy that is genuinely hard to picture, and it also generates a magnetic field of extraordinary complexity, one that twists, stretches, and reorganizes itself constantly as plasma churns beneath the surface. In certain regions, that magnetic field becomes especially tangled. Field lines get wound tighter than usual, stress builds, and the region becomes what solar physicists call an active region. These are the areas that produce sunspots. The darker patch is you. You may have seen in photos of the sun, which appear dark because the concentrated magnetic field suppresses the normal flow of hot plasma to the surface, making that patch slightly cooler than its surroundings. Active regions matter because they are the source of the 2 phenomena driving this week's events: solar flares and coronal mass ejections. A solar flare is a sudden, intense release of electromagnetic radiation, essentially a burst of light across the spectrum, from radio waves to X-rays. Flares are ranked on a lettered scale from A through B, C, M, and finally X, with each letter representing a 10-fold jump in energy. An X-class flare sits at the top of that scale, and within the X-class, the number after the letter indicates further multiples of that same energy. So an X5 flare releases roughly 5 times the energy of an X1. The most powerful flare on record occurred in November 2003 and was so intense it saturated the instruments designed to measure it, forcing scientists to estimate its true strength using indirect data afterward. Because a flare is essentially a burst of light, it reaches Earth in about 8 minutes, traveling at the speed of light. Its effects, mainly disruption to high-frequency radio on the sunlit side of the planet, are real but usually short-lived, lasting minutes to a few hours. The far more consequential threat, and the one behind this week's storms, is the coronal mass ejection, usually shortened to CME. A CME is not light, it is matter, an enormous cloud of magnetized plasma, sometimes weighing billions of tons, hurled outward from the sun's outer atmosphere. Unlike a flare, a CME travels at a fraction of light speed, typically somewhere between 400 and over 2,000 kilometers per second, which means it can take anywhere from about 15 hours to several days to reach Earth, depending on how fast it launched. When an Earth-directed CME arrives, it slams into the magnetosphere, the protective magnetic bubble surrounding our planet that normally deflects the constant stream of particles flowing outward from the sun, known as the solar wind. A strong CME compresses and distorts that bubble, and the energy transferred into Earth's upper atmosphere and surrounding space during that compression is what we call a geomagnetic storm. These storms are ranked from G1, minor, to G5, extreme. A G1 storm causes small fluctuations in power systems and pushes the aurora to around 65 degrees latitude. A G3 storm starts to create real headaches for grid operators, degrades GPS accuracy, and can bring aurora as far as 50 degrees, putting it within reach of places like northern Germany or the northern United States. A G5 storm, the top of the scale, can cause voltage control failures, push some grid systems toward collapse, render GPS effectively unreliable, and induce damaging currents in long pipelines and transmission lines. During true G5 events, aurora has been documented near the equator, which tells you just how deeply the planet's magnetic shield has been disturbed. This week's activity traces back to a single magnetically complex active region that space weather forecasters have been tracking across the solar disk for roughly a week and a half. The first eruption produced a strong X-class flare paired with a fast coronal mass ejection, captured clearly by coronagraph instruments, cameras that block out the blinding disk of the sun so the fainter corona around it becomes visible. When a CME expands outward in a full ring shape from the perspective of one of these instruments, it is called a halo CME. And it is one of the clearest signs that the ejection is heading directly at the observer, meaning directly at Earth. The most important piece of information about any incoming CME is something we cannot know until it is almost here, and that is its magnetic field orientation. If the CME's field arrives pointed opposite to Earth's own northward-facing field, the two connect and effectively short-circuit, dumping a large amount of energy into the magnetosphere. If it arrives aligned in the same direction, much of that energy gets deflected, and the resulting storm is far weaker. For this week's first eruption, the field turned unfavorable, and a confirmed G3 storm followed within hours of arrival. The second eruption, from the same active region, followed roughly a day and a half later this time, associated with an even stronger flare and a faster, denser CME. When a second, faster CME is launched along nearly the same path as a slower one ahead of it, something called a cannibal CME can occur, where the faster ejection catches up to and merges with the slower one during transit. The resulting merged structure tends to be denser, faster, and carries a more complicated magnetic field than either eruption would have produced alone, which makes its eventual impact considerably harder to predict, and often stronger than a simple sum of the two events would suggest. Forecast models tracking this week's sequence showed exactly that kind of merger taking shape during transit, and the resulting disturbance has been fluctuating between G2 and G3 levels, with the planetary KP index the standard global measure of geomagnetic disturbance, reaching 6 and 7 during the most active stretches. For context, the KP index runs from 0 to 9. A reading of 5 marks the threshold for a G1 storm. 7 corresponds to G3. 9 is the maximum, corresponding to G5. During the well-known geomagnetic storm of May 2024, the strongest since 2003, the KP index reached 9 and held there across multiple measurement windows, and people across the southern United States reported seeing aurora for the first time in their lives. Which brings us to the third eruption, the one drawing the closest attention this week. It came from the same active region as it rotated further across the solar disk, and it produced the strongest flare of the sequence, along with a CME moving fast enough that its transit time to Earth sits at the shorter end of what is typical. That matters enormously, because this CME is not arriving into a calm, fully recovered magnetosphere. It is arriving into a system still disturbed from the two impacts before it, a system whose protective response has already been taxed and whose ground-level induced currents have already begun stressing infrastructure. A strong CME landing in that already compressed environment carries a real possibility of pushing overall conditions into G4, or even G5 territory, the range where the word extreme in official severity descriptions starts to mean something concrete for power grids, satellites, and communication systems. To understand why that range matters so much, it helps to look back at two events that anchor almost every serious conversation about space weather risk: the Carrington event of 1859 and the Quebec blackout of 1989. In September 1859, British astronomer Richard Carrington was sketching sunspots when he witnessed a burst of intense white. Light erupt from the group he was observing, bright enough to see against the glare of the sun itself. He had unknowingly become the first person to observe a solar flare. Hours later, telegraph systems across North America and Europe failed simultaneously. Some wires threw sparks strong enough to set paper. A light? Some operators disconnected their equipment from its batteries and found messages could still be sent because the geomagnetically induced currents in the wires were strong enough to power the system on their own. Aurora during that event was reported near the equator. Retroactive estimates place its total energy at roughly 10 times or more above the strongest storms of the past century, based on ground magnetometer records kept at the time.